All right, so the last time that we chatted about this specific problem, this is example 4.8, we found that C3H6 must be the limiting reactant because it's present in less than its stoichiometric proportion in reference to both O2 and NH3. So from here we can now solve the problem. The problem wants to know what's the percent excess and what's the product composition going forward. So let's do that. So let's determine the excess of the non-limiting reactants in this case. So basically we're looking for what's NB stoichiometry, like based on stoichiometry, and NC. So if we react 10 moles of C3H6 with NH3, then we have 10 moles times the stoichiometric coefficient. So 1 mole of NH3 divided by 1 mole of C3H6 means that we're consuming 10 moles of NH3 every time we react this limiting reactant here. Let's move up just a little bit so I have some room. There we go. That means if we fed 12 moles of NH3, which is what we found in the first video, and we consumed 12 moles, that means we have 2 moles in excess every time those 10 moles react in this system. Let's try that for our other reactant. So if we react 10 moles of C3H6, I forgot my H6 here, there we go, with O2, then we have 10 moles and we multiply by a different ratio, right? Because the coefficients are different between these two. So 1.5 is the same as 3 halves, right? So 1.5 moles of O2 divided by 1 mole of C3H6 is going to tell us that we consume 15 moles of oxygen. This means if we feed 16.4 moles of oxygen, which is what we found in the last video, and subtract the 15 moles consumed, we have 1.6 mole in excess in this particular system. Oh, I'm sorry. Is it 0.6? No, 1.6. That's right. Sometimes math is hard, right? All right, now we want to find the percent excess. So if we're looking for percent excess, we take what's fed minus the stoichiometric amount and divide it by the stoichiometric amount, multiplied by 100%, and we find that there's 20% excess NH3 in this particular system. If we apply that same equation to O2, we take the 16.4 moles minus the 15 moles divided by the 15 moles times 100% to give us 9.3% O2 in excess. So that's going to solve that component of the problem. The last thing that we needed to do is we needed to find what is going on after that 30% conversion. We want to basically figure out how much is being generated. So I'm only going to solve for the ND2 and the NE3 because those are the two that really matter to us in this particular problem. So the problem says we have a 30% conversion of the limiting reactant. So we must know what the limiting reactant is in order to be able to do anything in this problem. So we're going to take 30% times the number of moles of this reactant. And then what we're going to do is we're going to say, well, if we look at the equation, for every 1 mole of C3H3N that's generated, we consume 1 mole of C3H6. That means that we generate 3 moles of C3H3N in our system, and that is ND2. So notice this isn't a flow rate, this is an amount. We can do amounts in our systems, right? So this is actually what's coming out in the system. It's kind of cool. Then, if we do the same thing and we say 30% of the limiting reactant again, but we look at water, the stoichiometric ratio of water to C3H6 is 3 to 1. So we then apply this, which means that we generate 6 moles of water, and that's Ne2 in this particular problem. Okay, so that's the idea here. A lot of using the stoichiometric coefficient, a lot of trying to understand how to apply all the components. So the 30% conversion must be applied to the limiting reactant, which means that we must know what the limiting reactant is. So as a quick review, the first thing we did, right, is we said, is our reaction balanced? Then we did what we always do. We drew a flow diagram and we chose a basis of calculation. Then we determined which species was the limiting reactant, and that allowed us to solve the rest of the problem. The problem was asking for the excess of non-limiting reactants, which we could find, and then how do we apply that 30% conversion to figure out what's going on in the system? So a lot of these extra steps is what makes a lot of these chemical types of problems so difficult. So make sure that you understood each of these steps because we're going to see them very, very often in a lot of these stoichiometric problems.